Hi, welcome back to my YouTube channel Easy Maths with Dr. Nasir, your path to maths confidence. In today's lecture, we will see initial value problems and exercises related to them. Nth order initial value problem. And nth order ODE d and y by dxn is equal to f of x, y, dy by dx, d2y by dx square up to dn minus 1 y by dxn minus 1, where x belongs to I subset of R, n belong to n, along with the initial conditions diy by dxi of x naught is equal to yi, where x naught belong to I closure, yi belong to R, I is 0, 1, 2 up to n minus 1 is known as nth order initial value problem, where f is a map from I cross omega to R. Omega is a subset of Rn. Also, d0y by dx0 is equal to y. Well, C an exercise. For C belong to R, the family of functions y of x is equal to 1 over 1 plus c exponential of minus x is a solution of the first order ODE dy by dx is equal to y minus y square. Find a solution of the first order initial value problem consisting of ODE 1.2 and the initial condition y of 0 is equal to minus 1 by 3. For the provided interval I subset of R over which the solution is defined. Well, C solution. Consider the given initial condition y of 0 is equal to minus 1 by 3. So 1 over 1 plus c exponential of minus 0 is equal to minus 1 by 3. So we have 1 over 1 plus c is equal to minus 1 by 3. Yes, taking reciprocal, we have 1 plus c is equal to minus 3. So c is minus 4. So solution of the ODE 1.2 satisfying the given initial condition is y of x is equal to 1 over 1 minus 4 exponential of minus x, which has domain minus infinity to log of 4 union log of 4 up to plus infinity. So I is minus infinity log 4 open interval because 0 belong to I. We'll see another exercise. For C belong to R, the family of functions y of x is equal to 1 over 1 plus c exponential of minus x is a solution of the first order ODE dy by dx is equal to y minus y square. Find a solution of the first order initial value problem consisting of ODE 1.4 and the initial condition y of minus 1 is equal to, for the provided interval I subset of R over which the solution is defined. Well, C solution. Consider the given initial condition y of minus 1 is equal to 2. Now using the function y of x, we have 1 over 1 plus c exponential of minus into minus 1 is equal to 2. So we have 1 over 1 plus c e is equal to 2. Just taking reciprocal, 1 plus c e is equal to 1 by 2. So c e is equal to minus 1 by 2. So c is minus 1 over 2 e. So solution of the ODE 1.4 satisfying the given initial condition is y of x is equal to 1 over 1 minus exponential of minus x over 2e. So this is 2e over 2e minus exponential of minus x. This function has domain minus 20 minus log of 2e open interval union minus 2 log of 2e up to plus infinity open interval. So I is minus log of 2e up to plus infinity open interval because minus 1 belong to I. Well, see another exercise. For C belong to R, the family of functions y of x is equal to 1 over s square plus c is a solution of the first order ODE dy by dx plus 2x y square is equal to 0. Find a solution of the first order initial value problem consisting of ODE 1.6 and the initial condition y of 2 is equal to 1 by 3. Further provide the interval I subset of R over which the solution is defined. Well, C solution. Consider the given initial condition y of 2 is equal to 1 by 3. Now using definition of y of x, we have 1 over 2 square plus c is equal to 1 by 3. So we have 1 over 4 plus c is equal to 1 by 3. Just taking reciprocal, we have 4 plus c is equal to 3. So C is minus 1. So solution of the ODE 1.6 satisfying the given initial condition is y of x is equal to 1 over x square minus 1. This function has domain minus infinity to minus 1 open interval union minus 1 1 open interval union 1 up to plus infinity open interval. So I is 1 to plus infinity because 2 belong to I. Let's see another exercise. For C belong to R, the family of functions y of x to 1 over x plus c is the solution of the first order ODE dy by dx plus 2x y square is equal to 0. Find the solution of the first order initial value problem consisting of ODE 1.8 and the initial condition y of minus 2 is equal to 1 by 2. Further provide the interval I subset of R over which the solution is defined. Let's see solution. Consider the given initial condition y of minus 2 is equal to 1 by 2. So we have 1 over minus 2 square plus c is equal to 1 by 2. So we have 1 over 4 plus c is equal to 1 by 2. So 4 plus c is equal to 2. So c is minus 2. So solution of the ODE 1.8 satisfying the given initial condition is y of x is equal to 1 over x square minus 2. We set domain minus infinity to minus 2 square root open interval union minus 2 square root to 2 square root open interval union 2 square root up to plus infinity open interval. So I is minus infinity to minus 2 square root open interval because minus 2 belong to I. Let's see another exercise. For C belong to R, the family of functions y of x is equal to 1 over x plus c is a solution of the first order ODE dy by dx plus 2xy square is equal to 0. Find a solution of the first order initial value problem consisting of ODE 1.10 and the initial condition y of 0 is equal to 1. Further provide the interval I subset of R over which the solution is defined. Well, see solution. Consider the given initial condition y of 0 is equal to 1. Now using definition of y of x we have 1 over 0 square plus c is equal to 1. So 1 over c is equal to 1. So c is 1. So solution of the ODE 1.10 satisfying the given initial condition is y of x is equal to 1 over x plus 1. This function has domain R. So I is equal to R. Well, see another exercise. For C belong to R, the family of functions y of x equal to 1 over x plus c is the solution of the first order ODE dy by dx plus 2xy square is equal to 0. Find the solution of the first order initial value problem consisting of ODE 1.12 and the initial condition y of 1 is equal to minus 4. Further provide the interval I subset of R over which the solution is defined. Well, see solution. Consider the given initial condition y of 1 by 2 is equal to minus 4. Now using definition y of x we have 1 over 2 square plus c is equal to minus 4. So we have 1 over 4 plus c is equal to minus 4. Just taking reciprocal, 1 over 4 plus c is equal to minus 1 by 4. So c is minus 1 by 2. So solution of the ODE 1.12 satisfying the given initial condition is y of x equal to 1 over x square minus 1 by 2. This function has domain minus infinity to minus 1 over 2 square root open interval union minus 1 over 2 square root up to 1 over 2 square root open interval union 1 over 2 square root up to plus infinity open interval. So I is minus 1 over 2 square root up to 1 over 2 square root open interval because 1 by 2 belong to I. Well, see another exercise. For C1, C2 belong to R. The family of functions x of t is equal to C1 cosine t plus C2 sin t is the solution of the second order ODE d2s by dt square plus x is equal to 0. Find the solution of the second order initial value problem consisting of ODE 1.14 and the initial condition x of 0 equal to minus 1 and ds by dt of 0 is equal to 8. Further provide the interval I subset of R over which the solution is defined. Well, see solution. Consider the given function x of t is equal to c1 cosine t plus c2 sin t. Just differentiating we have ds by dt of t is equal to minus c1 sin t plus c2 cosine t. Now using the given initial conditions x of 0 is equal to minus 1, ds by dt of 0 is equal to 8. we have C1 cosine 0 plus C2 sin 0 is equal to minus 1, minus C1 sin 0 plus C2 cosine 0 is equal to 8. So C1 plus C2 into 0 is equal to minus 1, minus C1 into 0 plus C2 is equal to 8. So C1 is equal to minus 1, C2 is equal to 8. So solution of the ODE 1.14 satisfying the given initial condition is x of t is equal to minus cosine t plus 8 sin t. This function has domain R, so I is equal to R. Let's see another exercise. For C1, C2 belong to R. The family of functions x of t is equal to C1 cosine t plus C2 sin t is the solution of the second order ODE d2 by dt square plus x is equal to 0. Find a solution of the second order initial value problem consisting of ODE 1.16 and the initial condition x of pi by 2 is equal to 0 and ds by dt of pi by 2 is equal to 1. Further, provide the interval I subset of R over which the solution is defined. Well, see solution. Consider x of t is equal to c1 cosine t plus c2 sin t. Differentiating, we have ds by dt of t is equal to minus c1 sin t plus c2 cosine t. Now, using given initial conditions x of pi by 2 is 0 and ds by dt of pi by 2 is equal to 1, we have c1 cosine of pi by 2 plus c2 sin pi by 2 is equal to 0 minus c1 sin pi by 2 plus c2 cosine pi by 2 is equal to 1. So we have c1 into 0 plus c2 is equal to 0 minus c1 plus c2 into 0 is equal to 1. So c1 is minus 1, c2 is equal to 0. So solution of the ODE 1.16 satisfying the given initial condition is x of t is equal to minus cosine t. This function has domain R, so I is equal to R. Let's see another exercise. For C1, C2 belong to R, the family of functions x of t is equal to C1 cosine t plus C2 sin t is the solution of the second order ODE d2 by dt square plus x is equal to 0. Find a solution of the second order initial value problem consisting of ODE 1.18 and the initial conditions x of pi by 6 is equal to 1 by 2 and ds by dt of pi by 6 is equal to 0. Further, provide the interval I subset of R over which the solution is defined. Let's see solution. Consider x of t is equal to c1 cosine t plus c2 sin t. Differentiating, we have ds by dt of t is equal to minus c1 sin t plus c2 cosine t. Now, using the given initial conditions x of pi by 6 is equal to 1 by 2, ds by dt of pi by 6 is equal to 0. We have c1 cosine of pi by 6 plus c2 sin of pi by 6 is equal to 1 by 2 minus c1 sin of pi by 6 plus c2 cosine of pi by 6 is equal to 0. So we have 3 square root by 2 c1 plus 1 by 2 c2 is equal to 1 by 2 minus 1 by 2 c1 plus 3 square root by 2 c2 is equal to 0. So we have 3 square root c1 plus c2 is equal to 1 minus c1 plus 3 square root c2 is equal to 0. Solving these for c1, c2, we have c1 is equal to 3 square root by 4, c2 is equal to 1 by 4. So solution of the ODE 1.18 satisfy the given initial condition is x of t is equal to 3 square root by 4 cosine t plus 1 by 4 sin t. This function has domain R, so I is equal to R. Well, see another exercise. For C1, C2 belong to R, the family of functions x of t is equal to C1 cosine t plus C2 sin t is the solution of the second order ODE d2 by dt square plus x is equal to 0. Find the solution of the second order initial value problem consisting of ODE 1.20 and the initial conditions x of pi by 4 is equal to 2 square root and ds by dt of pi by 4 is equal to 2 into 2 square root. Further, provide the interval I subset of R over which the solution is defined. Where C solution, consider x of t is equal to c1 cosine t plus c2 sin t. Differentiating, we have ds by dt of t is equal to minus c1 sin t plus c2 cosine t. Now, using the given initial conditions, x of pi by 4 is equal to 2 square root, ds by dt of pi by 4 is equal to 2 into 2 square root. So we have c1 cosine of pi by 4 plus c2 sin pi by 4 is equal to 2 square root minus c1 sin of pi by 4 plus c2 cosine of pi by 4 is equal to 2 into 2 square root. So we have 1 over 2 square root c1 plus 1 by 2 square root c2 is equal to 2 square root minus 1 by 2 square root c1 plus 1 over 2 square root c2 is equal to 2 into 2 square root. So we have c1 plus c2 is equal to 2 minus c1 plus c2 is equal to 4. So c1 is equal to 3, c2 is equal to 7. So solution of the ODE 1.20 satisfying the given initial conditions is x of t is equal to 3 cosine t plus 7 sin t. This function has domain R, so I is equal to R. Well, see another exercise. For C1, C2 belong to R, the family of functions y of x is equal to C1 exponential x plus C2 exponential of minus x is a solution of the second order ODE d2y by dx square minus y is equal to 0. Find a solution of the second order initial value problem consisting of ODE 1.22 and the initial conditions y of 0 equal to 1 and dy by dx of 0 equal to 2. Further provide the interval I subset of R or which the solution is defined. Well, see solution. Consider y of x equal to c1 exponential x plus c2 exponential minus x. Differentiating, we have dy by dx of x is equal to c1 exponential x minus c2 exponential minus x. Now using the given initial conditions y of 0 is equal to 1, dy by dx of 0 is equal to 2, we have c1 exponential of 0 plus c2 exponential minus 0 is equal to 1, c1 exponential of 0 minus c2 exponential minus 0 is equal to 2. So c1 plus c2 is equal to 1, c1 minus c2 is equal to 2. So c1 is equal to 3 by 2, c2 is equal to minus 1 by 2. So solution of the ODE 1.22 satisfy the given initial conditions is y of x is equal to 3 by 2 exponential of x minus 1 by 2 exponential of minus x. This function has domain R, so I is equal to R. Well, see another exercise. For c1, c2 belong to R, the family of functions y of x equal to c1 exponential x plus c2 exponential minus x is a solution of the second order ODE d2y by dx square minus y is equal to 0. Find a solution of the second order initial value problem consisting of ODE 1.24 and the initial conditions y of 1 is equal to 0 and dy by dx of 1 is equal to e. Further provide the interval I is subset of R over which the solution is defined. Well, see solution. Considered y of x equal to c1 exponential x plus c2 exponential minus x. Differentiating, we have dy by dx of x is equal to c1 exponential x minus c2 exponential minus x. Now using the given initial conditions y of 1 is equal to 0, dy by dx of 1 is equal to e. So we have c1 exponential of 1 plus c2 exponential minus 1 is equal to 0, c1 exponential 1 minus c2 exponential minus 1 is equal to e. So we have c1e plus c2 exponential minus 1 is equal to 0, c1e minus c2 exponential minus 1 is equal to e. So c1 is equal to 1 by 2, c2 is equal to minus 1 by 2 e square. So solution of the ODE 1.24 satisfy the given initial conditions is y of x equal to 1 by 2 exponential x minus 1 by 2 exponential 2 minus x. This function has domain R, so I is equal to R. Well, see another exercise. For c1, c2 belong to R, the family of functions y of x equal to c1 exponential x plus c2 exponential minus x is a solution of the second order ODE d2y by dx square minus y is equal to 0. Find a solution of the second order initial value problem consisting of ODE 1.26 and the initial conditions y of minus 1 equal to 5 and dy by dx of minus 1 equal to minus 5. Further provide the interval I subset of R for which the solution is defined. Well, see solution. Consider y of x equal to c1 exponential x plus c2 exponential minus x. Differentiating, we have dy by dx of x equal to c1 exponential x minus c2 exponential minus x. Now using the given initial conditions y of minus 1 is equal to 5, dy by dx of minus 1 is equal to minus 5. So we have c1 exponential minus 1 plus c2 exponential minus into minus 1 is equal to 5. c1 exponential minus 1 minus c2 exponential minus into minus 1 is equal to minus 5. So we have c1 exponential minus 1 plus c2 exponential 1 is equal to 5. c1 exponential minus 1 minus c2 exponential 1 is equal to minus 5. So c1 exponential minus 1 plus c2 is equal to 5. c1 exponential minus 1 c2 e is equal to minus 5. So c1 is 0, C2 is 5e exponent minus 1. So solution of the ODE 1.26 satisfy the given initial conditions is y of x equals 0 into exponential of x plus 5e exponent minus 1 exponential of minus x is equal to 5 exponential of minus into x plus 1, which has domain R, so I is equal to R. Well, see another exercise. For C1, C2 belong to R, the family of functions y of x equal to C1 exponential x plus C2 exponential of minus x is the solution of ODE d2y by dx squared minus y is equal to 0. Find a solution of the second order initial value problem consisting of ODE 1.28 and the initial conditions y is equal to 0 and dy by dx of 0 is equal to 0. Further, provide the interval I subset of R for which the solution is defined. Well, see solution. Consider y of x equal to c1 exponential x plus c2 exponential minus x. Differentiating, we have dy by dx of x is equal to c1 exponential x minus c2 exponential minus x. And using the given initial conditions y is equal to 0, dy by dx of 0 is equal to 0, we have c1 exponential 0 plus c2 exponential minus 0 is equal to 0, c1 exponential 0 minus c2 exponential minus 0 is equal to 0. So we have c1 plus c2 is equal to 0, c1 minus c2 is equal to 0. So c1 is 0, c2 is 0. So solution of the ODE 1.28 satisfying the given initial conditions is y of x equal to 0 into exponential of x plus 0 into exponential of minus x, which is just 0. This function has domain R, so I is equal to R. Well, in the next lecture, we will see some more questions related to initial value problems. If you have not subscribed my channel, Easy Maths with Dr. Nasir, your part to maths confidence, subscribe it now so you never miss a conceptual concrete lesson.